Welcome back. In this next series of videos, we are going to revisit the finite difference method. And specifically, we are going to explore the following topics. What do you do if you have a specified flow boundary condition? We talked about specified head and no flow. But what if you have a flow which is non-zero, such as an infiltration boundary? We're also going to look at how to deal with anisotropic soil, boundaries between materials, heterogeneous soils, so dealing with multiple materials. And then we're going to look at different solution techniques to solve your set of finite difference equations once you have them all set up. All right, specified flow boundaries. So in this case, we have a boundary where the flow is known but is not equal to 0. So you could say V is equal to Q divided by A. V would be the velocity, the flow velocity across that boundary. And to do this, we are going to, in this case, create an imaginary node which is labeled L. Kind of like we did in the previous video when dealing with no-flow boundaries. And we're going to go back to our basic equation that assumes kx equals ky and delta x equals delta y. And we know from Darcy's law, V equals minus ki minus k delta h over, or del h del x. And looking at flow in the horizontal direction, which is what we're doing here, the hydraulic gradient would be HR minus HL divided by 2 times delta, where delta is the spacing between two individual nodes. And so if you then multiply both sides by 2 delta and then divide by negative k, we get minus 2v delta over k equals HR minus HL. Remember, HL is our imaginary, is the head at our imaginary node. So if we solve for HL, that's equal to HR plus 2v delta over k. If we plug that back into our equation, we get 1/4 HR plus 2v delta over k plus HB plus HR plus HA. We actually could simplify this further by combining these two HR terms, but that, there you go. That's how you handle a specified flow boundary condition. Pretty simple and straightforward approach. Okay, what do we do if we have anisotropic soils, meaning Kx does not equal Ky? We mostly solve this in our earlier videos. Remember, our governing equation is right here. We have Kx times the second derivative of head with respect to x squared, Ky the second derivative of head with respect to y squared. From our earlier derivation in part 1 of our videos, we showed that the second derivative of head with respect to x can be approximated using this equation, HR plus HL minus 2HI over delta x squared. The second derivative in the y direction is HA plus HB minus 2HI over delta y squared. So we simply plug these two terms into this equation, and here's our governing equation based on these finite difference approximations of the derivatives. Now, we got to this point in our earlier lecture. The only thing we didn't do is solve this equation for h sub I. So if you solve it for h sub I, this is the general equation right here. It's definitely not as simple as our earlier case, although if we let delta x equals delta y, so a uniform grid spacing in the x and the y direction, then the deltas drop out and we end up with this equation, which again, not as simple as if it's isotropic, but still it's not too bad. So that is our equation for anisotropic conditions.